Hello, everybody. Well, for a precision timing guy, Lee, I'd call that a fail. Oh, there's a timer. Okay. All right, well, I pay no attention to that either. And, of course, first slide has a typo in it. That's not my email. I hope the last slide is correct. Anyway, hi, I'm Paul from TAG. Tell you a little story about an older standard that didn't really find any traction, and we did a little playing with it, and we found some useful ideas I'd like to share with you. So the SMPTE standard. This goes back to circa the 2000s, the nature of the problem and the beginning of this technology. The problem we were trying to solve was lip sync, which back in the day was problematic. SDI, of course, could readily get audio out of sync. You get it embedded out of sync, and it's stuck that way. MPEG-TS decoders were not always the most reliable at actually achieving or maintaining audio sync. So this was an issue. This was, in fact, apparently SMPTE's longest running ad hoc group. I inherited it from Graham Jones, who inherited it from someone else, and I don't even know how long it went. But my goal was to... Oh, time code's longer, of course, yeah. Time code will never end. Anyway, the whole idea with the study group was to look at the problem, the nature of the problem, the human aspects, the technical aspects, and the solutions available at the time to try and find something we could standardize. And after a whole bunch of this, we didn't really have much until Miranda came forward and said, we have this cool thing we did, and it seems to work pretty well. And that's the basis of this standard I'll talk about. Around 2010, this happened. In their prior testing and testing done by us at CBC Montreal, we found the solution to be sufficiently robust for the application. And although it was patented, Miranda happily offered us RAND terms as per SMPTE. So this was chosen as the basis for the standard. It's based on using fingerprints. And I want to point out that fingerprints are something you extract from something, and they're external. Right? Your fingerprints are in a file cabinet at police headquarters. They're not attached to you. A watermark is like a tattoo. It's attached to you. These are not watermarks. So we don't alter the content, which is really important. We don't want to ever touch the content. So instead, we extract them from the content and handle them as a sidecar. They're very compact with respect to media, very important. We want to have very lightweight things we can push around that aren't heavy. We want them to be robust to withstand any kind of intermediate processing, pretty much. Watermarks, for example, if you do scaling on a watermark image, you've probably lost the watermark. Again, reasons not to use that. They have to be efficient to generate and transport, and they have to be efficient to use in both matching and measurement. And we wanted to have media system-friendly transports. So agnostic to content, regardless of format, codec, or the transport, and resilient against video scaling, for example, on-screen displays, lower thirds, things like that, and audio parametric changes. If you're trying to do audio matching and somebody turns up the gain, I still want the matching to work. So 2064 is two standards. One is about generating the fingerprints. The other is about the transport for the fingerprints. And very well done. And it was published, done, and it sat there. Very lonely. A couple of companies did play with it. I'm not sure anybody's implemented a product on top of this at this point in time. But the problem with 2064, one of them is it doesn't do anything by itself. It generates fingerprints from content. Video frames, or God bless you, fields if you still have them, they generate one fingerprint each. Audio chunks of some size will generate one fingerprint each. And at the first point of generation, we assume AV sync is okay. This is key, right? If you have a sample where you know audio video sync is okay, we can now go through the system and compare against that. And then what? Well, downstream points, we generate these fingerprints again, and then we time compare them by some means to measure AV sync. So if audio is moved downstream with respect to video, we compare it to the head, we see them aligned, we see them unaligned, we can make a measurement. What the standard does not talk about is how to do this correlation, this searching, this matching, for a lot of reasons. Carefully choosing my words, at the time, there were individuals in the industry, an individual in the industry who had patents as his business. And within his portfolio, he had some patents related to audio-video sync we were very cautious about. And the correlation aspect was really of concern, and we didn't want to go near that. We felt that that was also the opportunity area for beneficial development on top of this standard. And that may have been one of the reasons the standard didn't go very far, is we didn't say what to do with these fingerprints, so we left it to people to sort of figure it out. Actually, I'll skip that. You know what that's about. Actually, I'll use it for a second. So some simple requirements. Lightweight data payloads, I mentioned, lightweight implementations, frame rate and format agnostic, mixed frame rates, and audio mixdown. So we do extreme data reduction on this fingerprint payload I'll show you shortly. The implementation of this algorithm is very simple in either VHDL or C. It was chosen for that reason and optimized, obviously, to put on a low-cost device. Multi-format, we're looking at pixels, but we're doing it based on geometry, not pixel lines and rows, right? Mixed frame rates we can handle because they have a cadence and they have a periodic alignment characteristic about them. No matter what the frame rate, there is some periodic behavior, so we can actually mix frame rates and still use this technology. And for audio, we simplified our life and we said basically take everything except LFEs and mix them down to a mono, generate one fingerprint for the audio. Nice and simple. There are some limitations to this standard. One is it needs motion. What we're measuring when we video fingerprint and you go to analyze them is we're doing a frame-by-frame comparison of fingerprints. If there's no motion, we have no interframe deltas to compare. So if there's no motion in the picture, whether it be a frozen image or whether it be black, we cannot do matching during that time. Audio needs dynamic sound. If there's no sound, we obviously can't match audio timing. And our algorithm is simple. We do a audio block-by-block comparison of peak against average level. Really quite a simple algorithm. But if you have no sound or a steady sound, then peak equals average. Again, nothing useful. So its universality as a test tool is not really strong. It will not work on bars and tone. Well, kind of the basic test case. But for monitoring program content, for monitoring streams, it's entirely adequate performance. Very rarely do you have long periods of freeze. Very rarely do you have long periods of silence. And during those, you simply don't make measurements. When they come back, you make your measurement. If everything's jumped, you deal with it. If nothing's jumped, you say, okay, it was just a holdover due to content. This is the simple model of the system. This is right out of the standard. And basically, we generate a reference fingerprint, and then we generate some downstream fingerprint. We do analysis, which gives us three things. It gives us an audio and a video delay. The difference between them is the lip sync. Very, very simple little model. For video fingerprinting, it's a simple little process, pretty much. We take any resolution we get, and we reduce it to an SD-like resolution. We pre-filter it so we make our lives easy. And then we do some windowing and subsampling. And this is kind of important. And this, for example, is out of the standard. This is 720p. And in the standard, we made what I think at the time was a mistake, but it was for clarification purposes. We actually specified pixel line and row numbers. The idea was we'd get away from the edges of the screen, and we'd have some number of sample points inside the picture, extremely low resolution, but represent, and filtered down, not just truncated, but actually, decimated, or actually more correctly, I guess, downscaled. And so we do this to provide us with a low resolution picture, and then we have a motion detection algorithm, which you'll see over here, and is basically a summation of difference. For audio, I mentioned we downmix anything that isn't a mono, or we take a mono, we do an absolute value, and then we just do two measurements. We do envelope average, and we do peak. I'm sorry, envelope is peak, mean is average, and we compare them. And it's a very simple way to characterize some audio and generate low bit rates. And then we decimate that down to a much smaller amount of data. The interesting part comes when we go to do the matching. And here's an example of, well, don't want to spoil the fun here. We have an example then of a sequence of video frames and a sequence of associated audio chunks. And just to make life simple to explain, I made the audio bundles of samples the same size as a video frame. And as you can see at the origin, they're all in sync. And somewhere downstream, after some delay, audio has gone early. Maybe there's been a couple of video frame delays in the way. This, by the way, is the worst lip sync ever. Everyone in this room is hearing me later than I'm speaking, right? There's latency built in. About 10 feet is a millisecond. So a bunch of you are, you're approaching half a frame away from me. But we can now use a sliding window correlator to find the difference. So that's exactly what we do. First, we correlate the video, because they're great big easy chunks. And we simply, whoa, Paul. Right. And we simply slide one of the samples along with respect to the other until we find a sequence of matches. And it can't just be one match. We're counting on an ongoing matching situation. And that's the strength of this in its simplicity, is the fact that if you can see a match on an ongoing basis, you know you're matched. If you see a brief match, you're not matched. It was coincidental. Obviously, if I reduce the data in the video to such a small amount, there's going to be many, many pictures that will make the same fingerprint. It's statistically almost impossible that a a minute of content, will have all the wrong frames and produce that exact same fingerprints as an unrelated video stream. So we correlate the video, and then we correlate the audio. And we do the same thing here. We slide the audio around until it matches, and we say, oh, hey, there's an AV delay. I simply slid my correlator window over that much. That must be my AV delay. Nice and simple. So in a system, it kind of looks like this. You can pretty much imagine what this is about, but basically we have the sync at reference point, and somewhere downstream we extract fingerprints again, and we send them somewhere to be correlated. And we use that mechanism to correlate them. So this is how the lip sync part works. So there's some added capabilities this needs, and this is what we maybe should have been documenting at the time, and we've learned thinking about this since. If you have that temporary loss of lock, there's silence, there's frozen video. You probably want some kind of holdover mechanism so your alarm doesn't fire on the very first frame of non-match video. You want to build in some kind of human parameter there that says, okay, if it's silent for 10 seconds, maybe that's a minor alarm. If it's 20 seconds, it's a major alarm. It depends on your content, right? Well, it's totally content dependent, but that needs to be tuned. Your window size. If your maximum latency you're expecting and could ever be possible is, say, 2 seconds, you don't want a 10-second window because your correlator will spend a lot of time searching. If you know it's never going to be more than 2 seconds, and in fact, if you know it's never going to be less than 1 second, you can set a 1 second wide window. Your correlator will find it fast when you go to acquire. And as well, there's a confidence factor involved here. When you do the matching, the fingerprints may not match exactly, but on an ongoing basis, they match very, very strongly. That confidence factor actually gives you a hint about the QoE. Right? So the picture is not as good as the source picture, but you've got an ongoing match. And when we look at the latencies we experience, I mean, in 2110, we have virtually no latency. Get down to HLS, you have some serious latencies, 6 seconds in this particular stream. So for this HLS, I mean, I have a 4 to 7 second window or something to limit my search times. So if we want to measure something like latency, how do we use this standard? Because, well, what is latency? Well, at the camera and mic, or on finished QC content, it's sound and light on a monitor and speaker. I know this is going to sound stupid, but let me keep saying it. At any point of later measurement and observation, it's again sound and light on a monitor and speaker. This is human latency in the terms the human can get it. I don't care what's happening in the stream. I care about what I put in upstairs and when I get downstairs and what that latency is. So really, latency is what a user can measure, see, hear, and quantify. This is what we want to measure if we want to measure latency. And I've tipped my hand as to where I'm going. Video frame boundaries are very handy points, by the way. They're highly periodic. They're very, very predictable and very tightly timed. And we need a time reference, but video frames aren't a time reference. So why is latency important? Well, as of 2 weeks ago, this is why latency is suddenly in the news and important. It was all over the front page of newspapers the day after the Super Bowl. And they call it drift, but it's absolute latency. And what's the problem? Well, you hear about people watching over the air versus watching OTT, and they hear their neighbors screaming for the goal 10, 20, 30 seconds, a minute before you see the goal. That's bad. Even worse, social media. If I'm sitting at the game and they score the goal, I can send a tweet in 2 seconds saying, he scored! So I'm the earliest news. Even the bettors have to work fast to keep, from catching up to me. Yet meantime, we're experiencing, so latency has become a very, very big thing. And optimizing and improving latency has become important to people. So we add a timestamp. Let's use an authoritative time reference to every fingerprint. Now, back in the day, this wasn't so much a thing. Today, however, you can have system-wide time at high accuracy. It could be PTP, it could be NTP. But something authoritative that's either a global time base or something that's private to you, as long as you have a consistent time base across your system against which you can measure things. So in this case here, that little oval is our little fingerprint. Boop. Again, little fingerprint container. Let's add a timestamp to it. Now how does it work? Well, we use the common time base to measure this in units of time. We're not going to measure it now in terms of arbitrary time. We're going to use real time to actually make numerical measurements. So we replace measuring between these 2 points with some local time, with some common time we can use across the system. So we've added a timestamp. I won't tell you what authoritative source we've used quite yet, but could be NTP, could be PTP, probably not PTP. Oh, okay, that was stupid. We decided to reduce the picture sampling to the safe action area according to SMPTE standard because that helps us rule out lower thirds and peripheral nonsense in the edge of the picture. We've defined the screen geometrically. We did that in the standard, but we actually expressed pixel positions because there were only so many video formats then. Hello, over the top. How many over the top variants exist in the world today? Hundreds, arbitrary resolutions. I mean, we need to define it geometrically and say, there's the part of this picture you're going to sample, regardless of your pixel resolution. We did some fine tuning of the algorithms, again, to better handle the OTT resolutions, because when you get way low in resolution, the fingerprints get a bit noisy. Discrete audio channels, in the standard, we've mixed them all down to a mono. Well, lots of people want to track inter-audio timing, not for sample accuracy for mixing a sound field, but simply for knowing a channel has gone wandering off. And we added a TCP transport. So we can now do some things like we can verify, on the right slide? Yeah. So we can now verify both the content and the latency throughout a system, again, using these fingerprints. We generate them where we know they're good, and then we measure them. So we can ensure the right content is in this position, and we can measure its latency. We can validate the right content is in this position, and the right content is here. We all know switching can go wrong, and the stream still has the same name and everything, just the wrong video's in the hole. And that can happen, right? So this is something that we can now do using time alignment of the, like real-time alignment of the fingerprints. We can do things like verification of ad insertion. We can watch for a SCSI trigger, and then we can watch to see that there was an associated change of content, because the fingerprint matches will suddenly end. Okay, the trigger was taken. Did the right commercial roll? Well, if we have an ad library of commercials and we pre-fingerprint the first 10 seconds of every commercial, and we know what's going to run, we can be ready for that new match the instant that commercial switches, and we can tell if the right commercial played. We could even, if you have that library and enough processing time, go and figure out what commercial played that was wrong. But at least it's a way of you understanding what's going on in your system. And even root cause analysis, just the fact that you can pull these things at every point in the system, see latency, and understand things are going where they're supposed to go, will help you zoom in. And you know, in a small system, in a TV station, maybe not such a big thing. If you're a global OTT distributor, this is a potentially large problem space. So this is a general system model, and I won't hype the product too much, but basically the way it works is we have a probing device and we have a management device called MCS. So we generate fingerprints in the real-time device, and we do the matching upstairs in the higher intelligence, in the media control system. And then that leads us to being able to deliver out of our database all of this information in near real time to give you the ability to go and do analysis on this stuff. And here's what it looks like. The SMPTE has been doing some testing. And in fact, they changed their live streaming work group's name to the latency work group just 2 weeks ago, partly in response to the Super Bowl thing, but in fact in response to a growing concern for this problem. But this is it in action, and this is using the SMPTE fingerprints with a few of the modifications I've discussed. And so we can actually measure live latency. This is frozen, of course. But we can measure live latency at a whole bunch of points. And this is latency with respect to T1, this picture here. So this stuff is working. We're still fine-tuning. There's lots of work to do to get this dialed in, really respond quickly, really match carefully, and so on. But it's very, very promising. What else can we do? Well, hey, why don't we add QoS and QoE metrics? We're touching every point with a fingerprint generator. Why don't we bundle in QoS and QoE information at the same time? Throw that around the system. So we can actually use this now as a handy point measurement tool to bring other metadata back to some common point where you can use that effectively. You can determine the quality of your content through yet another means that's simply camping on the back of this system. So, in conclusion then, 2064 gives you a sufficient basis for measuring latencies. That's pretty clear. The timestamps enables many more measurements to be made, which is really, really interesting, I think. We can add some QoS and QoE, and it comes for free. The transport is there. If you're doing QoE or QoS metrics, you can throw them into that same fingerprint payload, get them up to your central scrutinizer who can work with them. Maybe there's more. We'll see. And we've discovered some improvements can greatly increase the performance And we are, however, doing more testing and characterization to try and really make this thing super robust. Here's the question. Do we go back to SMPTE to revise 2064 with these improvements? Maybe we do an RDD because we don't want to go through the SMPTE time process, let's call it. Maybe we do a documented VSF or AMWA to reference 2064 and detail the changes and improvements there. What we'd like to avoid is 2 years, heaven help me, or the actual ad hoc group's 20-year life. We can't do that. We need to turn something fast. So I think we need to consider how we're going to publish these changes. We'd like to contribute them back to the industry and see if we can get more mileage out of this. So I'd be happy for anybody to tell me their opinion on this anytime. And I definitely think an EG or an RP-like document ought to be written as well, which was avoided with the original standard, and explaining just how you use these things and how you get benefit from them. And that's really all I have to say. And I have a minute or two for a couple of questions if anybody has any.
Excellent. Thank you very much, Paul.
Thank you.